So hi everyone, I'm Eric, and today I'm going to talk about the impact of formal verification on software development. And this is the work I've done with my collaborator at UCSD. So when I talk about formal verification, I'm going to focus on automated verification or autoactive verification, which is basically you write your code and you're going to write like pre and post conditions, so what should all that entry and exit of your function, and then this is going to get transformed by the verifier and then sent to a SMT solver that is going to tell you sad or unsad. And why I'm talking about this is because this is actually here, like in academia, but also in industry, and this is getting deployed with this critical systems such as like operating system or authorization protocol. And so why can we explain that like this thing is actually getting adopted? I would say two things. The first thing is like solvers are better than ever, and now also we have actually maintained verifiers that are actually used by industry. And so this is great, but yet automated verification is far from mainstream. And when you read the literature, you'll mainly see two things. The first thing being like, oh, well, there's still a huge amount of effort, and you'll often see at least this ratio of like 5:1, meaning 5 lines of proof annotation versus 1 line of code. And the second thing is the expertise. You need to be a formal method expert to actually use verification. And I want to come back on this because that's kind of what we hear, but it is a claim that is maybe not entirely true. And I think there's different kind of expertise. Yes, there's on one side the formal method wizard that will tell you like soundness is all I want to hear, I care about completeness and all these things, but there's also like another kind of expert, which is the hardcore programmer that would tell you like, what about the buzz factor? And this is a quote that I got from my study, which is basically what happened to this tool if the person that maintains it get actually hit by a bus? Who is going to take care of it? And this is something that they care about. So really different things that they care about when they actually write code, right? But one thing that they care, both of them, is they want the code to work. And actually, now with this kind of tools, automated verifiers, such as the one I'm going to focus on today, Dafny, both of these experts actually try to verify their code. So today, I'm going to try to give you like some experience on Dafny, but I hope that this is also applicable to other kind of tool, or even like if you're trying to design your own tool for verification. And so again, I want to focus on these experts. And for this, I want to take this user-centric approach and understand, okay, these people are writing software and they're trying to verify them with Dafny. So my question as a user study is like, what happened to software development now when you add formal verification? And so for this, I use a technique from social science called grounded theory, where we start by questions that we ask during sort of like semi-structured interviews. And then it ends up in a recording that is like around an hour long. We get a transcript, we try to annotate the transcript and analyze it. And from this analysis, we identify patterns and we refine the question and we iterate again and again until we kind of arrive to stable points where the patterns are the same. And so who did we ask this question to? Well, we had 14 participants, and we were really lucky because we had both these formal method wizards, but also this really experienced engineer. And we had an average of like 5 years of experience in the industry, with some of them being like actually in the industry since more than 10 years, and a wide range of domain for formal verification. And so what kind of question did we ask? Well, we went through all the stage of the development. The one we think about at first is which is like designing and building with like the specification, the proof, and the one that sometimes we tend to forget when we actually try to verify software, which is more like code review, testing, maintenance, what happened to my code after. And so what we do ask is like, okay, how do you go about specifying your code? Or like, what happened in your code once it is deployed? So these kind of questions. And so today, I'm going to try to give you a glimpse of some of the results that we discover by talking to people, to these users, and then trying to analyze the patterns. And so I want to come back to like, compared to regular programming, how does it differ or how is it sometimes similar? And so I'm going to talk about 3 things. For proof debugging, unlike normal debugging, it happens mostly in your head. There's no print in formal verification. And the second thing is proof hardening, which is similar to, I would say, a program where like a good proof is actually a simple proof to some extent. meaning that in the same way you would, like, if you have a big function in your program and you're going to try to, like, make it smaller and, like make it into multiple function, you would do the same for proofs. And the last one is code reviews, where, like, definitely spec, proof, and code is an information overload, and we need to rethink that. And so for the first one, for proof debugging, this is an example that I got from my user study where they basically try to, this method where they're really simple, they try to apply a discount on X with a certain percentage, and they have this precondition that is like, okay, X needs to be positive, and the percentage needs to be a correct percentage as a discount, and we want to show that the result is indeed positive. And so you can see the implementation here, it's quite straightforward, and what's happening when you try to verify this code in Dafny is you get an error message saying like cannot prove that the result is actually positive. And so when we ask the user, how do you react about these things, like what do you ask yourself, they will tell you like, okay, in this case, I'm asking myself like, who's wrong? Me or Dafny? Meaning like, is the program or the specification that I wrote wrong, or is it actually Dafny that is not able to prove this? And so how do they go about, so here they kind of rapidly rule out the I'm wrong, and they like try to understand why Dafny cannot prove this. And so how do you go about that? Well, the same way you do for programming, you would try to interpret the error message. And so let's see what the user reports when they read the error message. Well, right now, the thing just cannot tell you that 0.1 times 0.1 is greater than 0, which is quite like horrible. And they will think that this thing is kind of calling on an LM, but the thing is supposed to be good at math, and you have to give a better error message. And this is from like a hardcore engineer. They get really frustrated really fast about tool giving you this kind of answers. So okay, interpreting the error message didn't go so well. So what's the next solution? Because we cannot stay there, otherwise we cannot verify anything. The second thing is the sort of like active debugging, which they debug via assertion as breakpoints. And so here, what they're going to try to add is, for example, these assertions to kind of guide the solver through, to help the solver answer to prove that result is positive. And so here they try to add this assertion, but sadly, this is not enough. This is not what the solver needs. Indeed, and the challenge here is you need to actually build a mental model of the implicit verifier state. So what does the verifier knows, what does SMT know, and what it is able to infer. And what's needed here is that to say that the multiplication of two positive numbers is actually positive. And so as a sort of recommendation as a community, I think if we think about this kind of tool, we need to definitely kind of explicate this verifier state and define and visualize what the context is, especially if we're asking to a solver that is able to come up with more facts. So that's for proof debugging. So now we have the proof that worked at least once. Let's see if we can make it prove all the time. And you would ask yourself why? Well, because there's this problem of brittle proof. And so a brittle proof is a proof that previously verified, but where trivial and related change can cause the proof to fail. And this is because like the SMT solver is at the edge of what it can actually solve, and now you change the name of a variable, and the proof fail. And so the reaction of the users is quite a lot of frustration. One of the things they would say is like there's something soul-crushing about having to go back to things that you thought were done and do them again. But okay, so like let's try to understand what's the problem so we can actually fix it and make the proof robust, right? And so the main thing that a user report is the problem is the context. For the record, like in one of the projects, the amount of SMT queries that were sent to the solver was around 5 gigabytes. So I let you imagine the number of characters that 5 gigabytes represent, right? And this is, and on top of this, like this context gets blown up by quantifiers, but also like there's a ton of like visibility of the certain facts that shouldn't be included. And finally, in Dafny, like there's specifically this memory model with frame condition that can blow up your context. Okay, so now we have the problem, but the good news is there's actually a solution to this. And when we ask to developers, what they tell you is like, yeah, at first I had this problem, but now I think I can actually overcome it because it mainly requires discipline. And so what do they mean by this? Well, this is first a sort of extreme approach. I want Dafny to be as stupid as possible, make me really verbose, but make sure the proofs are easy for Dafny. And so you would think, okay, this seems like we're like back to proof assistant again, so what's the point of using Dafny anyway? Well, there's a sort of like less extreme approach, which is like, okay, if I don't play that game, if I'm in need to give more resources to the SMT solver, I just try to break it down to something that is actually reasonable for the solver. And since we talk about discipline, I think in engineering there's always a way, it's really important to think about a way to enforce this discipline. And so we need to think about like tooling or like ways to like prevent this proof from getting to the roof and have some kind of configurable linters. And finally, I want to talk about the code reviews and show that specification, proof, and code is information overload. So how does the normal code review happens? So the reviewer sees the code, and like classic reviewer would say, like, yeah, looks good to me, it's great, and we're done. Well, here it's completely different. Like we have not only the proof or the code, but we have also the proof, we have the specification, we have also the target code that is actually the one running. And so the reviewer is like, okay, there's so many artifacts, what should I look at? And what I should focus on? And so, again, what do the user report? Well, it's kind of a really mixed bag. They care about different things. Some people are telling us, like, the glorious thing about proof is that they are self-proving. There's no need to look about somebody else's proof. But just before I told you about like proof robustness, so actually people care about, some people care about looking at the proof because they want it to be robust and maintainable. Some other people would tell you like, well, reviews are the only time to check the pre and post condition are strong enough. So this is really the thing I'm focusing on because that's the moment I can check it. And finally, and maybe more surprisingly, some people care about the transpile code, the final artifact. Why? Because they work with other people, simply. And these other people don't formally verify the code. They run like the Java, they run like thing, and so they want the code, for example, to be integrated with theirs, and they also want the code to be performant, and that's dictated by the transpile code. So we should not forget about this. But what we should understand here, and I think that resonates with what I've been said yesterday at the keynote, is we need to have a way to focus on certain part of the code and like, let's say we have a specification. I want to look at the code that is linked to the specification and maybe not look at the proof. Or maybe actually I want to focus only on the proof because I want to focus this time on a path for robustness. And so we need to think like, what does it mean to toggle this focus while kind of like still keeping this sort of holistic view. And so finally, I want to finish by like trying, like, I hope I answered some of the question around like what happens to software development when you add formal verification. We were lucky enough to have these 14 experienced developers. We interviewed them with this method from social science, grounded theory, and today I give you a glimpse. I talked about like proof debugging, proof hardening, code reviews, but there's way more in the paper, and feel free to read it. Thank you.
Speaker. All right. Questions? Also, next speaker can come get set up.
Hi, great talk. I like this idea of a linter. Did you have any ideas of any specific like lint rules that a hypothetical linter would have?
So, I mean, I guess like for a lot of queries, like for a lot of code now, one example is like the visibility thing. And so you can have like function unrolling and like a lot of like function that get added into your context. And I think it like it would be nice to have like the linter tells you like, okay, this one is visible, and so it's added to your context, but you're actually never using it. So I think that's one thing. I think another thing, but has been done a bit, is like around unsat core, where it tells you like, okay, these facts are not needed, you can remove them, and so you could have like some linting around this. For now, it's like two different dissociated things. It's like just you run this like feedback with unsat core, but it's not actually in your IDE. So like people are not necessarily using it on the daily.
Yeah. Thank you.
Do you know if similar studies have been conducted for software developers who do not have prior experience with formal verification tools and trying to get them to adopt it, or seeing their reaction to it?
Can you repeat your question, please?
Have studies like this been conducted for examining software developers who do not have prior experience with formal verification?
So actually, in our study, when I talked about this engineer, hardcore engineer, some of them had no formal verification experience before, and they used the tool for the first time as like, yeah, like, I mean, my team goal is to verify this code or like to use Dafny, and so I need to get into it. And this is why we have like such reaction on like, why is it not able to like prove that 0.1 times 0.1 is greater than 0?
Thank you.
Here again.